In this video, we're going to take a look at solving logarithmic equations. So in the previous standard, we looked at exponential equations and we used logarithms in order to solve them. And so now we're going to look at equations that start out with logarithmic functions in them. So in example 1 here, we have the log base 3 of x minus 2 equals 2. Now, when we've worked with logarithms, we've often transferred from a logarithmic equation to an exponential equation, right? And so we know that that transfer looks like this, where we've got the log base b of x equals y, that is equivalent to the exponential equation b to the y equals x. So that right there is actually going to be our ticket to solving something like this. We need to get x by itself, and right now x is trapped inside of the logarithm. So how do you untrap it? Well, by writing an exponential form, that x will no longer be trapped in the logarithm. Right? So we know that we're going to take the base of the logarithm raised to what the log is equal to x minus 2. And we get 9, of course, is x minus 2. So we add 2 to both sides, so we get x equals 11. And that's our solution, but as you know, we always should, especially when we have new equations that we haven't solved before, we should definitely check to make sure that this answer makes sense. So if I go back to the original and I say, what is the log base 3 of 11 minus 2? Well, that'd be the log base 3 of 9, right? Which is asking us, what do I raise the number 3 to in order to make 9? Well, I would raise it to the second power, and that's exactly what I started off with on the right side of that equation. All right, so just at the top of this page, on the next page of the notes here, we have guidelines for solving logarithmic equations. So number 1 says to isolate the logarithmic term on one side of the equation, rewrite the equation in exponential form, which we just did, solve for the variable, and then number 4 says check for extraneous solutions. Now, some of the equations that we solved earlier in the quarter had what we call extraneous solutions. They had, or another way of saying it is they are fake solutions, right? Things that the algebra seems to spit out as answers, but they aren't actually solutions to the original equation. So we're going to take a look at that in this next example and see how that works. But look at number 1 here. It says isolate the logarithmic term on one side of the equation. We didn't really have to worry about that in the first example. But notice here, I've got logarithmic terms on the left side, but there's 2 of them, right? And number 1 seems to indicate that we just want one logarithmic term. And in order to use that transfer from a log equation to an exponential equation, we can only have one logarithmic term. So let's think back. What have we learned that could help us here? Well, one of the things that we just finished learning not long ago are special properties that logarithms have. So remember that if you have the log base b of a times c, then that can be written as log base b of a plus the log base b of c. So if I'm multiplying within a logarithm, I can separate it as 2 separate logarithms added. Well, the right side of this seems to be what I have here. So I should be able to go this direction and write these 2 logarithmic terms as a single logarithm. So according to this property, I should be able to say the log base 9 of x times x plus 2 is equal to 1/2. And now that I've established a single logarithmic term, now I can make my transfer to exponential form, right? So the base of the logarithm raised to what the log is equal to equals what's inside the logarithm. And this is something I can solve, right? 9 to the 1/2, that's just 3. Then we have x squared plus 2x. And then this is a quadratic, so we know that our job now is to get all the terms on one side, factor if I can. You know, if I need to, I can use the quadratic formula. I'm thinking this one has a decent shot at factoring. So x plus 3 times x minus 1, I think, should do the job. And so that gives us these two possible solutions here. X plus 3 equals 0, so x equals negative 3. And x minus 1 equals 0, so x equals 1. All right, so going back up to those guidelines at the very top of the page, right? We isolated the logarithmic term. We had to use a property of logarithms to do that. We rewrote an exponential form. We solved for the variable. But number 4, check for extraneous solutions. That just means literally check what you got back into the original equation. Make sure that it makes some sense. So we'll go over here for our check. So let's check x equals 1. So if I plug x equals 1 in, I've got log base 9 of 1 plus the log base 9 of 1 plus 2. And I want to know, does that equal 1/2? Well, the log base 9 of 1, remember that's what number do I take 9 raised to in order to make 1? Well, you take 9 raised to the 0 power, so this is 0. And then I have log base 9 of 3. Right, does that equal 1/2? Right, but the log base 9 of 3, I raise 9 to the 1/2, right, to make 3. So x equals 1 checks out, no problem. But when I look at the other one, when I look at x equals negative 3, I run into trouble from the very beginning because I'm going to take the log base 9 of negative 3 plus the log base 9 of negative 3 plus 2. And before I even really finish this statement, I know that I've got trouble because I know I can't take the log of a negative, right? That happens in both of these. Can't take the log of a negative. So that means that x equals negative 3 is not a true solution. So what we can say is x equals, I'll put that in a different color, I guess. We'll say x equals 1 is the only solution. Now, I went through and kind of checked x equals 1 from the very beginning until I got it down to saying the left side equals the right side. If you want to be a little lazier about this checking process, that's okay. The only thing that can really go wrong is to have you taking the log of a negative. And so if you're not taking the log of a negative, as I could see from the very first line here, that one's going to be an okay solution. It's just when we have the log of a negative that we're in trouble. Now, it's worth mentioning why it is that this happens. So, you know, here is really a negative 1, right? That's a negative 1. So we have the log base 9 of negative 3, log base 9 of negative 1. So where this extra solution, this extraneous solution comes from, is up here in this very first step. So if you were to put negative 3 right here and negative 1 in there, you've got two different terms that are impossible. However, consider what happens when you combine them and you have negative 3 here and negative 1 there. They multiply to become positive 3. So what's occurring is that you're only allowed to use this property. This is only true if A and C are both positive. And so that wasn't the case. We didn't know that it wasn't the case when we first started the problem, but it turns out when you're trying x equals negative 3, that wouldn't be the case. And so you never really should have used the property in the first place. But we have no way of knowing that, so we just go ahead and we use the property and then just make sure that we check our answers in the end. All right, so let's take a look at another one here. This one actually has a couple different ways you can approach it, and I'll go ahead and talk about both of them. So here we've got logs on both sides. Now, if we follow those guidelines from the previous page to the letter, it says that we should get our logarithm isolated on one side. Okay, and so since I have two logarithms, it probably makes sense to do something like this. Right? First start by just getting the two log terms on the same side. And at this point, you might be kind of thinking about properties, right? We know that we have a property that says this. I'm just running out of room here, sorry. That the difference of two logarithms can turn into the log of those two things that you're taking the logs of divided. All right, so we might want to use that. But let's understand that in both of these terms where we're subtracting, there's no coefficient in front of the logarithm. So this 2 is kind of a problem, but let's also remember that we have this rule, right, that says log base b of a to the r is equal to r times the log base b of a. So what I can do as a starting point here is get rid of this 2 by putting it up in the exponent inside this logarithm. So we can say the natural log of x plus 1 minus the natural log of x minus 1 squared equals 0. And then we've got the natural log of x plus 1 over x minus 1 squared using this property is equal to 0. Now, let's remember what the natural log means. The natural log is really the log base e of x plus 1 over x minus 1 squared. Right? And so you might find it helpful to go ahead and take the time to write that out, because that reminds you that when you go to rewrite it in exponential form, right, it'll be e to the 0 is equal to x plus 1 over x minus 1 squared. So to continue on here, e to the 0 is of course just 1. Right, and we know the drill. If we've got terms with x's in the bottom of a fraction, let's multiply by the least common denominator so that we can get that variable out of the bottom of the fraction. So multiply by x minus 1 squared on both sides. So we have x minus 1 squared equals x plus 1. But similarly to the last problem, we're just going to end up with a quadratic. So x squared minus 3x equals 0. So x times x minus 3 equals 0. And as I'm doing this problem, I should just apologize to you now for really not giving you enough room for this. But we get these candidate solutions of x equals 0 and x equals 3. All right, so do they work? Well, when we go to check this, if we plug in 3, we've got positive numbers on both sides. So that's going to check out. So that was checking x equals 3. But when we go to check x equals 0, we've got the natural log of 0 plus 1 on the left side, and that's fine, right? Putting a 0 in there is no problem. But over here it's problematic, right? Because we do get a negative in here. So that means x equals 0 is not a solution, because that's going to be negative. So x equals 3 is the only solution to this problem. Now there is a shortcut to this problem, but I wanted to do it this way to be really consistent with those guidelines I gave you, as well as showing you how the subtraction property of logarithms works here. But it would also have been okay, and I really don't have much room for this, I'm sorry about that, but it would also have been okay to use the property that the logarithm is a one-to-one function. In other words, that means that for any given y value of the function, there's only one x that goes with it. So using that idea, if I had just left these logarithms both on their respective sides, but I applied the power rule to the right side, the moment that I get it as the log of something equals the log of something else, because it's a one-to-one function, you can just drop the natural logs and just have x plus 1 equals x minus 1 squared, which is exactly where we ended up here after quite a bit of effort. Now, that's great if you ever have just a logarithm on one side and a logarithm on the other. Feel free to just use that property. However, understand that you won't always be able to do that. So make sure you're comfortable with this idea of applying the subtraction formula and then going from there. All right, so what I'd like you to do is we're going to do 2 more problems for practice here. I want you to try example 4 on your own, and then on the next page, I also want you to try example 5 on your own. So hit pause in the video, try both of these. They're applying what we've shown you in some of these previous examples, so see if you're starting to feel comfortable with this. All right, welcome back. So here, kind of like on that very first problem, we've got these 2 logarithms added together. So we want it to be a single logarithm. So let's try our property of x times x minus 3, right? Multiplying the 2 things we're taking logs of. And then there's no base written here, but remember that when there's no base written, it really means base 10, right? So this is going to be 10 to the 1 equals x times x minus 3 in exponential form. And so we get another pretty friendly quadratic equation. So x equals 5 and x equals -2. Those are just our candidates, right? But we got to check them out. So let's check x is equal to 5. See how that turns out. So I'm checking it back in the original, right? The very original. So log of 5 plus the log of 5 minus 3, right? Is that going to equal 1? Well, the answer is yes, that is going to equal 1 because they're both positive, right, inside the logarithm. So that's going to check out just fine. So let's check our -2, and we can see, right, without much effort, that that's going to be a problem. Right, since these are negative, that's not going to work out. So x equals 5 is the only solution to this problem. And then on example 5, I think here's where you can really see why it's really important to understand that you can move logarithms to one side and then apply properties, because unlike, let me go back to page 3 here, unlike this one where there's just logarithmic terms, so I could do this shortcut if I want, here because I have this non-logarithmic term, I really do want to subtract this to the other side so the logs can be on one side and the numerical part can be on the other. So the log base 3 of x plus 15 minus the log base 3 of x minus 1 is equal to 2. But at that point, I've got subtraction of logarithms with the same base. So the log base 3 of x plus 15, the one that's with the positive logarithm, and x minus 1, the one that's with the negative logarithm. And so we have 3 squared equals x plus 15 over x minus 1. Right, and then just like in that previous problem where we had subtraction of logarithms, we'll clear that fraction out. So 9x minus 9 is equal to x plus 15. And this one, we're just going to have a single solution, but we should still check it for sure. So subtract x from both sides. So 8x minus 9 and add 9. So 8x equals 24. So x equals 3. So is x equals 3 okay? Let's check on that. So in the original, log base 3 of 3 plus 15, does that equal 2 plus the log base 3 of 3 minus 1? And I could go through and, I could put that in my calculator, make sure the left equals the right and everything, that's fine. But the fact that these are positive means that we are okay. And x equals 3 is our solution. So as you're doing these problems and homework, remember you've got to always check your solutions. That's just a really important piece there whenever you're using those properties of logarithms, because those properties of logarithms, you're assuming, right, that each of these are positive up here when you use this property. And since right now it's an x, you don't know that what's inside of here is actually positive. So you always got to check those potential solutions.